Okay, now I'm going to repeat the lecture I did in class on Friday. That was the last day of February. We had some problems with recording the lecture that day. In the first hour, there was a power outage, so we couldn't complete the lecture. And then in the second hour, I had software problems. So at the end of the lecture, it turned out that the video was not recorded. So now I'm going to repeat the lecture again, and this time hopefully everything will be fine, and you will have a recording of that Friday's lecture. In fact, now I'm hoping that I have fixed all the issues with the software, so from now on everything will go smoothly. That's what I hope. And you will see the date and time of the recording here. So you see that today is actually a Sunday, and again I'm doing this recording at home all by myself. Okay, so let me just start. In fact, on Friday, all I did was I explained how the lift force is created, starting from the very basics. Okay, let me. So remember, I said for aircraft, the necessary force required to carry the weight of the aircraft can be created by using three different ways. The first one was static lift, and we call such vehicles lighter than air vehicles. The last one was where the engines are used to create a force in the vertical direction directly. And I said a very big majority of aircraft uses the dynamic lift concept. So that's what we will be studying in this course. So remember, I told you that in the dynamic lift case, dynamic lift aircraft needs to have a certain amount of forward velocity at least, such that this lift force can be created. Okay, so before I explain how that force is formed, let's go back to the basics. In fact, all the aerodynamic forces are nothing but pressure forces. Okay, so we live in the world where we are surrounded by the Earth's atmosphere, and every object exposed to air is under air pressure. So first, let's go through these definitions and understand how what air pressure is really. Let me just read through this definition here. A gas is composed of a large number of molecules that are very small relative to the distance between molecules. The molecules of a gas are in constant random motion and frequently collide with each other and with the walls of any container. So this is how a gas is defined. So I will start really taking some notes to further explain these concepts. Okay, so when we say we have a gas, basically we have a bunch of molecules that are far apart from each other, and these molecules are in constant motion. Okay, so I'm just throwing some random velocity vectors here. So assume that these molecules are moving in random directions. So this property of gases allow them to fill any container they are put in. So in other words, if some gas is released in a room, quickly that gas will fill the entire room. There will be a low concentration, obviously, but these molecules travel until they reach the boundaries of the container they are put in. So what that means is, if I have a container, let this be my container, and I have some gas in it, these are the molecules of that gas. So this is going to be air, obviously. So these are moving in random directions, and let's take a look at what happens when an air molecule hits the boundary. Okay, so let's say, so this is our molecule. So this keeps moving, and when it reaches the wall, it hits the wall and then it bounces back, right? So this is very similar to a ball hitting a wall and then bouncing back from the wall. So now let's take a look at what happens when it hits the wall. Okay, so I have before the impact, I have a molecule of some mass. It has a very tiny mass, and it's going in this direction. This is its velocity vector. And after impact, I have the same molecule moving in that direction, right? This is the velocity vector of the molecule after the impact. So remember, at the beginning of the lecture, at the beginning of the semester, I told you that the Newton's laws of motion are the basis for most of engineering stuff, and particularly in this course, it's very important. So even at this level, even at the molecular level, you see that these laws of motion are can be used to explain what's happening. Okay, so if you look at what's happening here, there is a certain velocity of this tiny air molecule, and after the impact, it has a different velocity, right? So the velocity has changed during this collision. In other words, there's a delta velocity here. And this is the difference between the new and the old velocities. And we can do this vector subtraction graphically. So I have this okay, so this is my V2 vector, and I have the V1 vector. Since I'm going to subtract the V1 vector, I need to change the direction of the arrow. So this is minus V1. This was V2. And if you so this is my delta V vector. Okay. So this is the change in velocity during the collision. So a change in velocity means there was an acceleration, right? So if you remember the second law of motion, it says if an object is acted by a force, then that object will go through an acceleration, or this works both ways. That means if an object accelerates, then that means an external force must have been applied to it. So if you write acceleration as the time rate of change of its velocity, and since we have a non-zero delta V here, that means we have an acceleration that can be quantified with that expression. Okay, and the second law says that there's such a relation between the force and acceleration, and since we have a non-zero acceleration and there's such a force that must have been applied on this air molecule, and this force is applied by the wall during the impact. Okay, so we can say that since delta V is in this direction, the force must be in the same direction as that. So let me just draw that. So there's a force in this direction. So this is the force applied by the wall on the air molecule, and the same force in the other direction must have been applied by the air molecule on the wall, and this is due to the third law of motion, which is the action-reaction principle. So and let me use red color for that. So this is the reaction force applied by the molecule okay, so now I think I can add some more explanation to this by typing some explanations here. Okay, at any instant millions of molecules hit the surface, and the total of applied force on the surface, the sum of all these forces form the pressure force. Okay, so let's go back to the PowerPoint presentation. Okay, so the second bullet explains what I just explained. As the gas molecules collide with the walls of a container, the molecules impart momentum to the walls, producing a force perpendicular to the wall. The sum of the forces of all the molecules striking the wall divided by the area of the wall is defined to be the pressure. Okay, so this is how the pressure is formed. So, in fact, any object surrounded by a gas is under this pressure. Okay, so anything within the atmosphere feels this pressure. So this includes all of us, right? So we are surrounded by air, and we constantly get hit by air molecules, and this pressure is really applied on us. But the thing is, if the surrounding gas is stationary, is steady, then these pressure forces are the same at every point on the surface, and then they cancel each other out. So there's no net force. There's no the total of these forces becomes zero. So let's consider a pen, right? So if you have such a pen, this gets this pressure, but the pressure applied on this side gets cancelled by the pressure applied on the other side. So note that all these arrows should have the same length, meaning that the magnitude of these forces are the same. So when you add all these forces, you don't get any net force. So this is true for an aircraft that's not moving. So let me go back to this picture here. So I showed you this picture before. In fact, I have a video of that. So let me quickly find that video. So in this video, we see the takeoff of Airbus A380 aircraft from this airport. So this is a part of the certification process. Remember, in our previous lecture, I showed you the certification videos for rejected takeoff of Boeing 777 and Airbus A340 aircraft. So this is another test performed for certification. So this test basically performs how aircraft takeoff performance is at very cold weather conditions. So this place is in Canada. So it's the northmost airport on the earth. So the average temperature is very cold, and they're doing this test at that airport to show the cold weather performance of this aircraft. So anyway, at this point, the aircraft is moving very, very slowly. Okay, so this is almost equivalent to having a steady, a stationary atmosphere around it. So at every point around on the surface of the aircraft, there's a pressure force, and this pressure force is symmetric. The pressure distribution is symmetric everywhere, so there's no net force. Okay, so let's see. Let me take forward this video, and the aircraft starts accelerating, as you see. So it gets faster and faster. So what's happening here is the aircraft starts moving through a stationary atmosphere. Okay, so the atmosphere is still stationary, but the aircraft starts moving through it with an increasing speed. Okay, so when that happens, when the air starts flowing through an object with some speed, then the pressure distribution changes. Okay, so the pressure distribution is not symmetric anymore, and unlike the stationary case, there we can have some net force, net pressure force. Okay, so let me just talk about that a little bit. Okay, so as I said before, every single part of the aircraft is subject to air pressure and produces some aerodynamic force. But in this course, we make the assumption that the entire aerodynamic forces are created by the wings only. So from now on, I will ignore the rest of the aircraft and I will concentrate on wings only. So we will only be talking about what's happening on the wings. And when you look at a side view of the aircraft, you see the wing. And let me go back to my drawing here. So this is my aircraft. I have this vertical stabilizer, and when you look at from the side view, you see the wings cross section, and we will be concentrating on this part only and ignore the rest of the aircraft. And this shape here, which is the cross section of a wing, is called an airfoil. Okay, so so normally as you see in this video, this wing, this airfoil is moving through the air, right? So let me just go back to the video again. And as you see here, the wing keeps moving through the air. So this is what's really happening for an observer fixed to the earth. So for an observer fixed to the earth. But if you are fixed to the airplane, what you will see is that you have your airfoil here, and you see the airflow is coming through your aircraft, right? Okay, so again, if you are an observer fixed to the airplane, you see the airfoil as stationary, and you will see the air coming towards your airplane. So this is for an observer fixed to the aircraft. And obviously this V should be the same V as before. So this is the speed of the aircraft, and an observer fixed to the airplane will see the air coming to him at the same speed. Okay, that's very good. So far we said that we explained how a gas applies pressure to a surface, and then we said that if you have an aircraft moving through with some velocity, this is what you have. Okay, so let's see what happens here. So this is our airfoil, and the airfoils typically have such a shape. And let me tell you what's special about this shape. If you look at the lower surface is more or less flat, okay? But if you look at the upper surface has this curvature. So this is pretty typical for an airfoil. And let's see how this special shape affects the airflow. Okay, so we have these airflows coming towards our airfoil, and if you look at these streams of air, you see that they have a more or less unobstructed path, so they can just go through the lower surface, right? They have nothing blocking them. But if you look at these streams of air, it's not the case for them, right? So the airfoil is a solid object. Air cannot go through the airfoil. So what happens? So these streams of air need to somehow find their ways around the airfoil. So they cannot disappear. They cannot go through the airfoil. So they have to find their ways around the airfoil. Okay, so these ones will be more or less going without any difficulty, whereas these are just the paths of airflow. So this airstream will have to do something like that, right? And this has to do something similar. So I should have used a different color for all these. In this case, these should be red as well. Okay, so if you see what's happening here, the air coming here needs to get squeezed due to this curvature of the upper surface, right? So they have to go through a narrower region here, whereas the air going through the lower surface does not have to go through such a narrower opening. Okay, so at this point I think I can go on with this video. So let me just play this video. This video, as far as I remember, is a pretty old video. You can actually tell from the recording. So this is something like 40 or 50 years old video prepared by FAA, I guess, this American Federal Aviation Administration. Just an explanatory video about the lift force. So let's play that.
By animation, let's study the airflow in greater detail. First, note that its pattern suggests it is passing through a tube-shaped device. Next, notice that the entrance and exit of the device are the same size. We can measure the openings and find that the ends are each 10 square inches. The middle part is squeezed, creating a throat of 5 square inches. Now, if we direct smoke lines through the device, its pattern will show that something happens to the air where it goes through the narrowed part. What we find is that when the airspeed is 100 miles an hour at the entrance of the device, it is also 100 miles an hour at the exit. Yet at the same time, the speed at the narrow part is considerably higher. It can easily be understood, therefore, that the air increases in speed as it passes through the smaller opening. But the interesting thing is that in order for the air to go at the faster speed through the narrow part, something has to balance this change in velocity, this speed difference. What changes is the
Okay, so in the video, he says two things. He says that if an airflow through a channel has to go through a narrower opening, it turns out that its speed increases. So this is one information. And the other information is if the speed of the flow increases, then its pressure drops. So this is the second information. Okay. So let's think about that, these two pieces of information, and let me try to convince you that they are in fact true. So let's start with the first part. Let's think about if the flow speed really increases if it has to go through a narrower opening. So in fact, you already know this from your daily experiences, right? So imagine water flowing through a hose, and let me show you the video for that. So you know from your daily life experience that if you squeeze the end of the hose, you will force the water to leave the hose at a greater speed, and you do that to such that the water will shoot out to farther distances, right? So it's a pretty short video, but this lady is doing what I just explained. So she squeezes the end of the hose, and that forces the water to leave at a greater speed. So this is really very easy to understand. If you force a flow to go through a narrow change, then the flow should accelerate. But the second part may not be that obvious. So if the flow accelerates, then why should its pressure drop? Now let's think about that a little bit. Okay, so at the beginning I told you that gas molecules have these random motions, right? So they move in these random directions. But when you have a flow of this gas, what happens is each molecule has this random velocity plus the velocity of the mean flow. So if the gas is flowing at some speed v, let's say this is the speed vector, then each molecule will have this speed vector added to its random velocity. And then the speed of each molecule will be the sum of these two, right? So this will be flowing, going in that direction, this is going in that direction, this is going in that direction. So what I'm saying is, let me come back here. You see, I showed these lines. These lines show how these air streams move. So even when it's going through this path, there's still some random small velocities around that mean trajectory, right? So this red shows the mean trajectory of the flow, which is formed by this red vector. But on top of that mean trajectory, there's still these little variations happening. So by the way, I just noticed that I did it wrong here. So let me just fix it so that it won't be confusing for you. So I should be adding them, right? So this should be like that. So anyways, so the air molecules here go through this path, but at the same time they still have these tiny velocities which cause them to strike the surface. Okay, so the air molecules are following this path, but at the same time they still keep hitting the airfoil. Okay, so let's keep that in mind for a while, and now let me come back to my presentation here and move on to this next slide, where you see animation of an airflow around an airfoil. So this is the airfoil. So let me just stop the animation for a while. Okay, so if you see that you have a uniform flow coming here. So at this point we have a uniform airflow. That means every stream of air has the same velocity in the same direction. But as they approach the airfoil, as you see here, they have to change, obviously, since they cannot go through the airfoil. So some streams go from above the airfoil, and some of them go underneath the airfoil. And as you see here, the air molecules going through the upper surface accelerate. So let's take a look at these dots. Okay, so they are moving in parallel, but as they approach the airfoil, watch what happens to this one going above the airfoil. And this is, remember, these two were moving in parallel, so they were moving in parallel, but now this one has gone through the airfoil, whereas this lower one is still close to the airfoil. So this is because the upper one is going much faster, as you see here, right? So the upper one goes much faster than this lower one. So this is obviously a computer animation, but this animation is consistent with what we said before. Okay, now let me stop the video again, and let's say that each one of these dots contain a certain amount of air molecule. Okay, and now let's count the number of air molecules on the upper surface and on the lower surface. So unfortunately I cannot use my pointer while the animation is stopped. So I'm just going to count the number of dots on the lower surface. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, now there are 18 little dots on the lower surface, and the number of dots on the upper surface is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 dots on the upper surface versus 18 dots on the lower surface. That means at any instant, number of molecules on the upper surface is much less than number of air molecules on the lower surface. That means the upper surface will be getting hit by air molecules far less compared to the collisions, air molecule collisions on the lower side. And this means the pressure on the upper surface is lower with respect to the pressure on the lower surface. And this means that there will be a net force in the upward direction, and this net force is really what we call this lift force, dynamic lift force. Okay, so when there is no airflow, when the air is stationary, the pressure is the same everywhere. Okay, so this second curve I drew represents the air pressure. So the length of these arrows are the same. So my drawing is not very accurate, but assume that this arrow has the same length and this arrow, and the forces are the same everywhere. So this is the stationary case. But when there's an motion, it's not the case anymore. So the pressure force on the upper surface is smaller, whereas the pressure force on the lower surface is greater. And if you sum all these little forces, you will see that so in this case, a net force is created in upward direction. And we call that upward force lift force. So we don't really call that force directly the lift force, but in other case, in upward direction, which forms the lift force. Okay, so this is pretty much what I covered in class on Friday. So hopefully, this video has been recorded without any issues, and so this video covers the Friday's lecture. Okay, so on Tuesday I will continue from here, and I will be talking about how this force is quantified. So now this just explains that a net force can be created when there is motion, and the airfoils are designed with a special shape that allows the air to flow at different speeds on the upper and lower surfaces. And starting from Tuesday, I will be talking about how this force can be quantified, because we need to put this force into numbers so that we can calculate the performance of our aircraft. Okay, so I'm going to stop here. Okay, I stopped the recording, but then I remembered that I showed some additional stuff in class that day, so I'm doing an additional recording to show that additional stuff. Well, I showed you this animation. This is just an animation. And I tried to convince you that there will be lower pressure by just counting these dots here, which I created in this animation. What I showed in class that day is I showed you some actual video from a wind tunnel test. So let me now play that video here. So this is an actual wind tunnel test recording. And they used smoke to make these air streams visible. Otherwise, you can't really see the airflow. Air is not really visible. But when you inject these smoke particles into air, you can see the flow, and which is what they did here in this video. Okay, now they're sending pulses of smokes. So you can assume that each one of these line segments include a certain equivalent amount of air molecules, more or less equal amount of air molecules. And as you see, the flow is pretty uniform here. So, and let's see what happens at the next instant. Okay, they approach the airfoil. Now, so the same thing is happening, obviously. These the streams have to get divided into two, since they cannot go through the airfoil. Some of them go from under the airfoil and some of them go above the airfoil. Okay, so this stream was parallel with this one here, but at this instant, look at that. So this is at a much forward position. Okay, so this stream is still stuck at this part of the airfoil, whereas this other stream covers almost the entire upper surface. So that means on the upper surface we have this stream, but now on the lower surface this has the same molecules as this one here, and now there are additional air packets that we cannot see from the previous pulses. Okay, so the previous pulses, we didn't see the previous pulses, but here there must be much more air molecules. So what I'm trying to say here is the previous, this was a computer created animation, whereas this is an actual wind tunnel test, and this proves that this is consistent with the other animation, that at any time instant the number of molecules on the lower surface is much greater than the number of molecules on the upper surface. Okay, so this was one other thing I showed in class on Friday. And then I showed you this other video. Well, a lot of the things that I talk about in this class can be observed very easily. So you don't really need some fancy laboratory equipment to see the effect of all these things. And this is a very good example. So here they prepared a very simple experiment set up for a little girl. And now the girl explains what's happening.
They made an experiment with a bit of piece of paper, sticky taped it together, and then we had to sticky tape a straw to it, and then we had to sweat a piece of steam through, and then we had to turn on the fan and see if the straw went up to the stick. And now, okay, Maine, go away. There it goes, up the top of the string. Up again, down.
Why is it going up?
It goes up because the air pressure is lighter on the top.
So as you see here, you can do an experiment to show how lift force is created very easily. You don't really need anything special except for a little fan. You can just make a small wing out of paper, and then, in fact, I did this at home myself, and it works really well. So hopefully you will take time to do this experiment and then record it and share the video with the class. It will be a very nice thing to do.